Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with your same module, that is database design concepts, and the same chapter, that is the chapter number 9, that is the relational query languages. In the last class we have discussed about the various operations that is performed on the relational algebra, as well as what is the formal definition of the relational algebra. Now today I am going to continue with the same module or the same chapter, that is the relational query languages, but not on the relations but on the table, that is but on the, we can say, the rows, that is a tuple relational calculus. In till now we have discussed about the relational calculus or the relational algebra. Now next is the tuple relational calculus, that is what are the various operations that will be performed on the tuples, that will be performed on the rows, that is the tuple relational calculus. So first is formal definition of the relational algebra. That is, what is the formal definition of relational algebra? That is the operation that is performed, tell you a complete definition or complete description of an expression in the algebraic algebra. So whenever we use the relational algebra, that can be used for giving the complete definition of the expression that is used in the relational algebra. A basic expression, that is a basic statement or the basic expression in the relational algebra, consists of either of the following. So whenever we write any expression for the relational algebra that contains the following fields, that is what is a relation, that is the name of the table that is used, that is a relation in the database, as well as the constant relation. So what is the relation in the database and what is the constant relation? And the constant relation is written by listing its tuple within the curly braces. So we apply the curly braces and the tuples are listed out, we can say the rows are listed out. For example, this is the example, that is 222, that is the ID, then Einstein, then physics, and 95,000. In the same way, next one is ID, then Sing, then finance, then 80,000, and the curly braces will be closed. So these are the two groups, these are the two, we can say the IDs, we can say the number that will be allotted. So we can either represent within the brackets by listing its tuples. That is a constant relation, and the relation is simply a table that will be performed or that will be representing in the database. A general expression in the algebra is constructed out of the smallest sub-expressions. These are the various smaller sub-expressions. We can apply the union, we can apply the minus, we can apply the Cartesian product, that is multiplication. There is a select statement, there is a project statement, and where is P is a new name, that is rows for the result even. So these are the various fields that is used for the various edges, that is used for the various relations. So next is additional relational algebra operation. That is, what are the additional algebra relation that is available in the relational algebra? So what is the operation that would be used in the relational algebra? So this is one of the tasks, that is a set intersection. So we have discussed that is how to use the set intersection, or what is the relationship between the set intersection and the intersection set. So the first additional relational algebra operation that is defined is the set intersection, that is denoted by the reverse U. So this is the example that is given. So this is the example, that is finding the course ID or displaying the course ID. We can say the field attribute where the semester equals to 4 and the year equal to 2009. Note that we can rewrite any relational algebra expression that uses set intersection by replacing the intersection operation with the set of the, or with the pair of the set difference. Operations such as R intersection S is equals to R minus S. Therefore, set intersection is not a fundamental operation and does not add any part to the relation algebra. It simply provides or simply gives more convenient way to write the R intersection S than to write R minus S. So this is very better to write the set intersection, that is finding the intersection between the R values and the S values. Then next addition operation is natural join. That is how to maintain, or what is a natural join? That is a binary operation that helps you, or that helps us to combine certain selections and the Cartesian product into one operation. So whenever we want to apply multiple methods on one operation, or we can say the multiple selections in one operation, that will be done by the natural join, and it is denoted by the join symbol, that is like this one. This is join symbol. The natural join operation forms a Cartesian product of its two arguments. So that forms a Cartesian product means combination of the two relations, combination of the two arguments that is given, that is representing in a Cartesian product. This is one of the example, that is a natural join of the instructor relation with the teacher's relation. Till here this is the instructor table, and till from here this is the teacher's table. So one is the instructor, then is the teacher's table, that is done by the natural join. This is also one of the query that is associated with the natural join, and therefore the natural join is also known as the associative. Then you discuss about the assignment operation, that is what is the assignment operation, how it will be used. So at time assignment operation is denoted by the arrow that works like the assignment in a programming language. So if I want to assign some value, if I want to give some value, that will be represented by the, we can say, the left arrow, or we can say the opposite arrow, that is just like a assignment operator that is used in the programming language, any programming language. So for natural join we use the operator, this is the operator that is used for the natural join. Then outer join operation, that is also an extension of the join operation to deal with the missing information. Suppose there is some instructor who teaches no course, then the tuple in the instructor relation for that particular instructor would not satisfy the condition of a natural join with the teacher's relation, because there is no teacher available, there is no, we can say, the tuple available in the instructor relation that teaches the physics, so that condition will not be satisfied. So then we use the outer join, that is outer join operation, that is very similar to the natural join, but we but preserve only those tuple that will be lost in any join, or in a join, by creating the tuple in the result containing the null value. So whenever we use a null value, that will be represented by the outer join. And there are multiple outer joins that is available. One is the left outer join, then right outer join, then full outer join, and then all these forms of outer join are available that computes the join, and the instructor will be used, or the instructor and the, we can say, the teachers table will be appearing figure 6.17 and the figure 6.18. Then next is one by one we have discussed about the left outer join, then there is a right outer join, full outer join. Then next is the extended relational algebra operation. That is, what are the extended relational algebra operation that is available. So one is the generalized projection, that extends the projected operation or the projection operation by allowing the operations such as arithmetic and the string function to be used in the projection list. So that is a generalized projection, that is how to use the arithmetic and the string function that is to be used in the projection list. The generalized projection operation has the form. So this is the form that is used for the generalized projection. Then next is the aggregation, that is also an extended relational algebra operation, that is takes a collection of the values and returns a single value as a result. So it takes multiple value and return a single value as a output as a result. That is the aggregation function. Then we have discussed about the what is the relationship between the multiset, or what is the multiset relational algebra, that contains multiple set, or it's a version of the relational algebra that works on the multisets, or that works on the multiple, we can say, the multiple relations. That is the set that contains various duplicates, or the set that contains various rows that have a same value or the duplicate values. And the basic operation that is used in the are as follows. We have discussed about these basic operations, that is how to use the multiset operation in the relational algebra. Then we have discussed about the relationship between the, or comparison between the SQL and the relational algebra, that is what is the SQL and what is the relational algebra, and what is the relationship, what is the comparison between the SQL and the relational algebra. This is select A1, A2 till N from R1, R2 till Rm, where P is a condition, we can say the P is a predicate. That is the SQL and the relational algebra. Then next is the tuple relational calculus. That is the next topic. That is the today's topic. That is how to use, or what is a tuple relational calculus. That is a calculus, or we can say the expression that will be operated on the tuple, that will be operated on the rows. That is a tuple relational calculus. So when we write a relational algebra expression, we provide a sequence of the procedures that generates the answer to our query. So when we write the relational algebra expressions, or when we write any expression that is available in the relational algebra form, we provide a sequence of the procedures, we provide a various sequence that generates the answer to our query. The tuple relational calculus, be contrast, or we can say the by contrast, is a non-procedural query language. So the tuple relational calculus is the non-procedural query language. It is not a procedural query language, but it is a non-procedural query language. But the relational algebra that we have discussed, that is operated on the relation, that is a relational algebra, that is a procedural query language. But this is a non-procedural query language. It describes the desired information without giving a specific procedure for obtaining that information. That is, it describes or it obtains a desirable information or the desired information without seeking out or without giving a specific procedure for obtaining that information. That is, there is no information that is available, simply obtaining the function, simply obtaining the desired information without giving a specific procedure or without giving any procedure for the information. Then a query in the tuple relation is expressed. So how a query is expressed in the tuple relation? So there is a T, there is a PT. That is, it is a set of the tuples, that is a T, so that the predicate P is true for the T. That is a PT means a predicate, that is a condition that is true for the T, and T is a set of the all the tuples, that is a T. Following are the earlier notation that we use TA to denote the value of the tuple T on the attribute A, and we use TER to denote the tuple is in the relation R. So this symbol denotes that the tuple T is belonging to that relation or belonging to that table. So the TER, that is a tuple T, is in relation R. Before we give a formal definition of the tuple relational calculus, we return to some of the queries for which we wrote relational algebra expression in section 6.1.1. So how to use them, or how to use the relational calculus that is used, that is denoted by the relational calculus, that is denoted by the tuple relational calculus. Before we give a formal definition of the tuple relational calculus, we return to some of the queries for which we wrote a relational algebra expression in section 6.1.1. So before giving a formal definition how to use the tuple relational calculus, we return to some of the query, we'll give some of the query and write the relational algebra expression that is denoted in the various form. Now these are the various examples, or we can say that these are the various queries that is denoted by the tuple relational calculus. That is how to use the tuple relational calculus, what is the main difference between the relational calculus of the relation and the tuple relational calculus. So this is the example of the query. So this example says, find the name, ID, department name, salary for instructors whose salary is greater than 80,000. So what are the various attributes that is finding out? That is any ID, that is a name, that is a department name, that is a salary. For whom purpose or for which table? That is the instructor table, where the salary is greater than the 80,000. The salary is greater than 80,000. This is denoted by, this is T, that is a tuple, all the tuples of T. Then T arrow or TE instructor, that is what is a condition, that is a tuple is belonging to the instructor table, that is the row is belonging to an instructor table. And what is the condition? So this is the AND, this is the condition that the T salary, that is the tuples of the salary, is greater than the 80,000. So finding the ID, finding the name, finding the department name and the salary as well from the instructor table, but the condition is that salary is greater than the 80,000. That whatever the salary, that is greater than the 80,000, that is the T salary is greater than 80,000. Suppose that we want only the ID attribute that is given, that is only the ID attribute that is given in this one, rather than all the attributes of the instructor relation. So whatever the attribute, whatever the table that is denoted, we want only the ID attribute rather than all the attributes. To write this query in the tuple, we need to write an expression on the schema ID. So we use the schema, we use the attribute that is the ID only. So only one attribute is required, that is the ID. We need those tuples on the ID such that there is a tuple in the instructor with the salary is greater than 80,000. So what is the request, or what is we can say the query that is available. So there exists is also used. So this is known as the there exists, that is the tuple is exist in the instructor. So express this request, we need the construct there exists for mathematical logic. This is the there exists, then there is a t, then belongs to the r, then qt. That means there exists a tuple t in the relation r such that the predicate q is true. So whenever I want that there exists, that will be denoted by the reverse e. That is the reverse e t that belongs to the relation r, where qt is the predicate, qt is the, we can say, the condition, whenever the condition is true. Using this notation, we can write the query, that is find the instructor ID for each instructor with a salary greater than 80,000. So finding out the instructor ID, we can say the finding out the ID for each instructor with a salary that is greater than 80,000. So this is given, that is a T, then there exists a S that belongs to the instructor, where the TID equals to the SID. So that is the ID of the T and the ID of the S will be same, where, and what is the condition, that is the S salary is greater than 80,000. That is the salary of the S is greater than the 80,000. That is also a condition. In English, we read the preceding expression as the set of the old tuples T such that there exists a tuple S in the relation instructor for which the values of T and the S for the ID attributes are equal. That is simply an English statement that is given, and the values of S that is given for the salary purpose, for the salary attribute purpose, that is greater than 80,000. So first of all, there is a tuple there, that there exists a relation, there exists a, we can say, the relation of the or S that belongs to the instructor, where the ID of the T and the ID of the S are matching, and condition is that S salary is greater than the 80,000. Tuple variable T is defined as only the ID attribute. Since that it is the only attribute having a condition specified for, therefore the result is a relation on the ID. Now consider the query. Finding the names of all the instructor whose department is Watson building. This query is highlighted more complex than the previous one because it contains two relation, two tables, that is the instructor and the department. So there exist clauses in our tuple relation calculus that is denoted or that is connected by the and sign. This is the and sign. Now this is the T, that there exists a S that belongs to the instructor, where the T name equals to the S name, and arrow U that belongs to the department, where the department name of one instructor, or where the department name of one table, that is a U, belongs to the department name of the next table, that is a S. And what is the condition? That is the building name equals to Watson. So these are the three conditions, these are the three margins that will be used. So first one is related to the instructor table, then the second is related to the department table, and the third condition is that building equals to Watson. This is the name of all the instructors whose department is in the Watson building. Tuple variable U is restricted to the department that are located in the Watson building, while the tuple variable S is restricted to the instructors whose department name matches to that of the tuple relation U. Figure 6.21 shows the result of the query. So what is the result? That the building name equals to this one, building name equals to this one. Now to find the set of all the courses that is taught in the fall 2009 semester and the spring 2010 semester, or the both, so we use the union operation, that is a combination of the both, that is the fall 2009 and the spring 2010. In the tuple relational calculus, we shall need to there exists clause that is connected by the or sign, right? So there is a T that exists, that there exists S that belongs to the section, and the T course ID equals to S course ID. So course ID from the T is equals to the course ID from the S, and condition is that, or and there is a S semester equals to fall, that is the semester equals to fall, and year equals 2009. Or there exists U that belongs to the section, where the course ID of U is equals to the course ID of T, and the semester is equals to spring, and the year equal to 2009. So this is the condition. One is using the section, one is using the section for course ID, and there is a relation, that is the OR relation, where the either the both the systems, or either both the, we can say, the seasons, both the semesters, either one of the semester, that is of the fall or the spring semester. This expression gives us the set of all the course ID that is given for at least one of the following holds, that is, that contains one of the following holds, that is, the course ID appears in some tuple of the section relation with semester equals to fall and the year equal to 2009. So whatever the course ID that is given, that is equals to some of the section relation, some of the fall relation. If the same course ID is offered in both the fall 2009 and the spring 2010 semesters, if the same course ID is applied to both the semesters, then its course ID appears only once in the result. That is, if there is a duplication, if there is a, we can say, the comparison that is performed on the fall 2009 and the spring 2010 semester, so its course ID appears only once in the result, because the mathematical definition of a set does not allow the duplicate number. That is, there is no duplicate number that is available. The result of this query appeared earlier in figure 6.5. Now this is another, we can say, the example that is given. So for the except purpose, we use the not sign. So there is a or sign that is denoted by the V, and there is an and sign that is denoted by the reverse V, and there is a not sign that is denoted by the arrow symbol, or we can say the dash symbol that is available, that is a not symbol. This tuple relational calculus uses that there exists as there is a section, then there is a dot 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 close to require that a particular course ID is taught in the fall 2009 semester, and its use of the there exists u that is belong to the section. The query that we consider next uses implication that is denoted by the arrow sign. So the formula, that is P arrow Q, means P implies Q. That is, a P implies Q means there is a P that exists for the Q. So there is a P implies Q. That is, if P is true, then Q must be true. So if the P is true, then Q must be true, otherwise the Q is false. Note that P arrow Q is logically equivalent to the note of P and V, or we can say the and V. The use of implication rather than not and or suggests that the more intuitive interpretation of a is required in the English that is given. And whenever we want to give the full or construct, that is denoted by the this symbol. So these are the various notation that is given in this. Now next is the formal definition, that is what is the formal definition of the relational calculus, or what is the formal definition of the tuple relational calculus that is available. So this is the tuple relational calculus, and what is the formal definition, that is a P, and there is a slash, there is a PT. So T is the, we can say, the tuples of all the rows, or we can say the rows of a relation, and PT is the predicate, that is what is the predicate that is available, where P is a formula. Several tuple variables may appear in the formula. A tuple variable is said to be free variable unless it is quantified by the there exists, or the we can say the V, reverse V, that is denoted by this one, that is the for all. So there exists in the for all. Therefore T there belongs instructor, and there exists S belong to department, where department name equals to T of department name equals to S of department name. So T is a free variable, tuple variable S is said to be bound variable. A tuple relational calculus formula is built up out of the atoms. An atom has one of the following forms. So what is the form of the atom? That is one of the following form that is available. Now what is the safety of the expression? That is how safety will you produce for the expressions? So there is one final issue to be addressed. So there is one final issue that is to be addressed over here. A tuple relational calculus expression may generate an infinite relation. That is, there is an infinite result, that is an infinite, we can say, the query that is formed, that is an infinite table that is required. So suppose that we write the expression, that is a T, then there is a slash, and there is a note, T arrow instructor. So there are infinitely many tuples that are not in the instructor. Most of these tuple contains value that do not even appear in the database. Clearly, we do not wish to allow such expression. That is, there is no provision that is available for the expressions. To help us define a restriction of the tuple relation calculus, we introduce the concept of the domain of a tuple relational formula. So what is the concept of the domain that is available? Domain is a tuple relational calculus, that is a domain. And typically the domain P is denoted by the domain, that DOMP, that is a set of all the values that is referenced by the P. So what is the all the value that is given? So it is a set of all the values that is referenced, that is given by the P. They include the value that is mentioned in the P itself, as well as the value that appears in the tuple of a relation mentioned in the P. Therefore, the domain of P is a set of all the values that appears explicitly in the P, or that appear in one or more relations whose names appear in the Phi. So for example, if I am repeating or I am doing DOM, that is a domain of T belongs to instructor, and the T salary is greater than, or the T salary is greater than the 80,000, that is a set containing 80,000 as well as the set of all the values appearing in any attribute of any tuple in the instructor relation. So we say that an expression T arrow P is safe if all the values that appears in the result are from the domain P. So domain is nothing but we can say that the block of the, like a block of the programming, that is from which the values are arrived, that is the domain. Now next is the expressive power of language, that is what is the expressive power of language. The tuple relational calculus that is restricted to the safe expression is equivalent in expressing or expressive part to the basic relational algebra. So tuple is very restricted to the safe expressions with the basic relational algebra, that is the union, minus, multiply, select, project, but without extending the relational operations such as generalized, projection and the aggregation. So therefore for every relational expression using only the basic operation, there is an equivalent expression in the tuple relational calculus, and for every tuple there is an equivalent tuple or relational algebra expression. So there is a relational algebra expression, there is a tuple relational calculus that is available. Now next is the domain relational calculus, that is what is the domain? A second form of relational calculus that is appear in the domain relational calculus. So we have covered with the tuple relational calculus. Now next is the domain relational calculus, that is we can say the block relational calculus. So the second form is domain relational calculus, that uses the domain variables that takes on the values from an attribute domain. So what is the attribute that is given? That is the attribute that is coming from the domain rather than the values for an entire tuple. The domain relational calculus, however, is closely related to the tuple relational calculus. So whatever the domain calculus or whatever the domain relational calculus that is available, that is closely related to the tuple relational calculus. So this is closely, or this we can say that there is a direct relationship between the domain tuple calculus and the domain relation calculus or the tuple relation calculus. Domain relation calculus serves as a theoretical basis of the widely used, or serves as a basis of the widely used, we can say the QBE language. Just as the relational algebra, that is this is the query based language or query based engineering that is available, that just as a relational algebra serves for the SQL language. Now what is the formal definition for the domain calculus or domain relational calculus? So this is the formal expression. This is given where the x1, x2, x2, xn, and there is a predicate and there is a symbol sign, or there is a, we can say the symbol sign that is available between the x1 to the xn and the p, then x1, x2 till xn, where x1 till xn denotes or represent domain variables. So these are the various domain variables that start with the x1, then x2, then till xn, and the p represents the formula that is composed of the atoms, as was in the case of the tuple relational calculus. So P is the, we can say the atoms, we can say the that represents the formula that composed of the atoms. An atom in the domain relational has one of the following forms. So what the P values is, that is depends on the atom. This is x1, x2 till xn, then x arrow y, then c. And then we build the formula for this one, that is a formula that is also available for relational calculus, that is how to use the formula or how to use the relational calculus. I'm just coming within 2 minutes. After that we will start again the session, so just coming within 2 minutes. Now again start the session. So we can build the formula with the help of the following rules. What are the following rules for obtaining the formula in the domain relational calculus? First of all, first rule is that atom is a formula. So whatever the atom that we are using, that is a formula. If P1 is a formula, so our note of P and the P1. So there is a note of P that is also available and the P1 is also available. And if P1 and P2 are the formulas or formulae, that so we are P1 arrow P2 or P1 and P2, P1 or P2 and the P1 arrow P2, that is it belongs to the P2. And if P1x is a formula in the X, so if P1 is given as a formula in the X, where X is a free domain variable, then there exists a X, so that P1x and for all X there is a P1x. So that is represented by this one, that is there exists, as well as the for all that is also given in the P1x. That are also the formulas. As a notational standard or shorthand, we can write there exists ABC, P ABC for all. There exists B, C and then P ABC. Now example queries, that is what are the various queries, that is example of these queries. We now give domain relation calculus queries for the example that we considered earlier. Now what are the various examples? The first example is that find all the instructors or find the instructors ID, name, department name, salary for the instructors whose salary is greater than 80,000. So whatever the salary that is given, that is greater than the 80,000. So finding the instructor's ID, that is ID of the instructor, name of the instructor, department name and the salary for the instructors whose salary is greater than 80,000. Right. So this is written as this one. There is an arrow that is given. There is an arrow. Then there is a I N D S. That is the ID, then name, then department name, then salary. And there is a slash, or there is a, we can say the rotation, where the INSD is greater than E instructor, that is this belongs to the E instructor. So what is the syntax? This is the syntax. So these are the various, we can say the domain variables, and this is the represent the formula. So this is a variable, or this is, we can say the represent the variables, and this is the formula that is given, that is the IND is less than E instructor ID, that is also given for this one. Then and there is a salary, that is a S, that is a greater than the 80,000. Now next example is that find all the instructors ID for all the instructors whose salary is greater than 80,000. There is a N that belongs to that there exists IDS, that is available, and condition is that IDS belongs to the instructor that is greater than and S is greater than the 80,000. Although the second query appears similar to the one that we wrote for the tuple relation calculus, there is an important difference. In the tuple calculus, when we write there exists x for some tuple variable s, we blind it immediately to a relation by writing there exists s that belongs to the r. However, when we write the not belongs to n, or there exists a n in the domain calculus, n refers not to a tuple but rather to a domain value. So what is the domain value that is given? That is belonging to the domain value. Therefore, the domain of the variable n is unconstrained till the subformula, that is INDS, that is greater than the E instructor that contains n to the instructor names that appears in the instructor relation. Now we now give some examples of queries in the domain relational calculus. Now finding all the instructors, or finding the names, or find the names of all the instructors in the physics department together with the course ID of all courses that they teach. So what's the course ID? What's the we can say the department that is given, that is the course ID of all the relations. So there is a NC, then there exists IA, such that ICASY is greater than the teaches, then and there exists DS, then INDS is greater than the E instructor, and the D is equal to physics. Now next is finding the set of all the courses that it taught in the fall 2009 semester, for spring 2010 semester, or both. So there is a C, then there exists S, then CASYBRT, then there is a section that, and then S full, then Y equal to 2009. Then there exists U, that is CASYBRT, that is greater than the section, and the S equals to spring, Y 2009. So this is the finding the set of the courses or finding the relation that is taught in the fall 2009 semester and the spring 2010 semester. Now next is find all the students who have taken all the courses offered in the biology department. So this is the I, then there exists N, then DT, I and DT, then there exists a student that is also available over here. Now next is the safety of the expression, that is what is the safety that is available. So we noted in the tuple relational calculus it is possible to write the expressions that may generate an infinite relation. So if there is a exists that exists in the infinite relation, that is also a safety that is also provided. This led to or that led to the defined safety for the tuple relational calculus expressions. A similar situation arises for the domain relation calculus like INDS, then that belongs to the node INDS, then there is a instructor. That is unsafe because it allows values in the result that are not in the domain of the expression. So for the domain relation calculus, we must be concerned about also about the form of the formula that within there exists and for all clauses. So there is a x, then there exists, then y, then xy that belongs to r, then there exists z, xz that belongs to r, and p xz. So p is some formula that involves the x and the z. And it is safe for the following holds. So these are the following hold that is available to be safe. So the all value that appears in the tuples of the expressions are the values from the domain, that is a dom p. And for every there exists some formula for the form, that is there exists x p1x, the some formula is true if and only if there is a value x in the domain p1. So if there is a value that is available in the domain p1, so whenever that is a condition is possible such that the p1x is the true. And for all sub formula of the form, for all x p1x, the sub formula is true if and only if p1x is true for all the values x from the domain p1. Now the purpose of the additional rule is to ensure that we can test for all and there exists sub formula without having to test infinitely many possibilities that is available. Now so for there exists x p1x is true, we need to find only one x for which the p1x is true. In general, there will be infinitely many values to the test. So all the domain relation calculus expression that we have written in the example queries of the section are safe, except for the example unsafe query that we saw earlier. Then the next is expressive power of languages. That is, what is expressive power of language that is available. So when the domain calculus is available, or when we represent the domain calculus that is available over here, it is restricted to the safe expression. So it is equivalent in the expressive part to the tuple relational calculus that is restricted to the safe expressions. Since we noted earlier that the restricted tuple relational calculus is equivalent to the relational algebra, all three are the following are the equivalent. So all the three are of the form that is equivalent, that is available. So what are the various values that is equivalent? The first one is the basic relational algebra. Then second one is tuple relational calculus that is restricted to the safe expression, and the third one is domain relational calculus. That is the first is the basic relational algebra that we have discussed. Then next is the tuple relational calculus that is restricted to the safe expressions. Then next is the domain relational calculus that is restricted to the safe expressions. So one is the basic relational algebra, then tuple relational calculus, then there is a domain relational calculus that is also available for domain calculus operations. Now we note that the domain calculus also does not have any equivalent of the aggregate operation, but it can be extended to support the aggregation and extended it to the handle arithmetic expression is straightforward. That is there is a straightforward that is also available. Now we have finished with this chapter, so let's start with the summary. That is, what is the summary all about, or what the summary says, or what is the main logic behind this chapter. So first point says the relational algebra defines a set of algebraic operations that operates on the table. So whenever we use the relational algebra that defines a various algebraic expressions, we can say the algebraic operation that can operate on the table. and the output tables as their result. So it contains or it operates on the tables or also contains output that also contains as a or also contain their result. These operations can be combined. These operations can be combined to get expression that expresses the desired query. The algebra defines the basic operations that is used within the relational query languages. So what is the relational algebra that is available? That contains the algebraic operation, that contains the algebraic, we can say the operation that is used within the relational query languages. Now what are the operations that is used in the relational algebra? That can be divided into basic operations. One of the operation of the relational algebra is the basic operations, then arithmetic or additional operations, then extended operations. The relational algebra is a terse formal language that is inappropriate for the casual users of a database system. Commercial database system therefore uses language or use language with more syntactic sugar. The next point is the tuple relational calculus and the domain relational calculus are non-procedure query languages that is used. So one is the tuple relational calculus, one is the domain relational calculus, that are the non-procedure query languages that represents the basic part that is required in a relational query language. The basic relation algebra is a procedural query language. So one is a procedural language, two are the non-procedural language. The tuple relational and domain relational are the non-procedural languages, and the relational algebra is a procedure language that is equivalent in part to both the forms of the relational calculus when they are restricted to the safe expression. The next is the relation calculi are the terse formal language that is inappropriate for the normal user or the casual user of the database system. Now, next is the review terms. That is, what are the review terms of this chapter? Then these are the practice questions that is available, and these are the various questions that is available on the tuple calculus, domain calculus that is available over here. And these are the various exercises that is available over here. This is the bibliographic notes. Now we have finished with the chapter number 6. That is now come to the part 2. So we have finished the part 1. That is what is the introduction to the, we can say, the SQL, then advanced SQL, then we can say the relation query languages. Now next is the database design. That is a part 2. How to design the database, that is the database design, and the next chapter, that is the database design and the ER model. So now our focus is moved to the designing part. So we have finished with the analysis part. Now we move to the designing part. That is a part 2. So let's take a break right now, then move to the second part, that is a part 2, that is the database design. Right. So let's take a break right now. So come back from the break. Now let's start the session again. So let's start with the part number 2, that is a part 2, that is a database design. So we are finished with the part 1, that is the basics of the, or we can say the introduction to the database. Now next is the database design, that is a part 2. So this is just a designing process, or we can say the picturization process, we can say the pictorial process by which we can design the database, by which we can represent the database. So that is a database design. This says database systems are designed to manage large bodies of information. So what is the database system that are designed, or we can build the database, we can make the database to design or to manage the large bodies of information, or to collect or to manage the large bodies of the information. These large bodies of information do not exist in isolation. So whenever we apply the large bodies of information that do not exist in the isolation, that is, do not exist in a single, they are a part of the operation of some enterprise whose end product may be the information from the database of the some device or service for which the database plays only a supporting role. The first two chapters of this part focus on the design of the database schema. So first two chapters that focus on the database schema. The entity relation diagram or the model that is described in chapter number 2 is a high level data that is model. Instead of representing all the data in a table, it differentiates between the basic objects like entities and the relationship among the objects. And this is the first step that is used in the database design, we can say the database schema design that is available. So it is often used as the first step in the database design or database scheme design. Relational database design, that is a design of the relational schema, was considered informally in the earlier chapters. There are, however, principles that can be used to differentiate good database design from the bad one. So what are the good database design, what are the bad database design? That also forms, so chapter number 8 describes the formal design of the relational schema. So this chapter simply gives the schemas, or we can say the designing of the database. What are the various designing of the database, whether it may be a relational schemas, whether it may be a normal forms, whether it may be a database design schema. The design of a complete database application environment that meets the needs of the enterprise being modeled requires attention to a broad set of issues that may be covered in chapter number 9. So whatever the designing phase, whatever the design, that is a complete database application environment that meets the needs of the enterprise, that is model, that also gives an issue that is explained in the chapter number 9. This chapter first covers the design of a web-based interfaces to the application. The chapter then describes how large applications are architected using multiple layers of the abstraction that is given. Finally, this chapter provides a detailed discussion of security at the application, what are the security provisions that is available, and the database levels, that is what are the various levels of the database. Now, let's start with the chapter number 7, that is the database design and the ER model. That is what is the database design and what is the ER model that is used in the database design. So chapter number 7, that is the database design. So up to this point in the text, we have assumed a given database schema and studied how queries and the update are expressed. That is how the queries and how the updates are expressed. We now consider how to design a database schema in the first place. That is how to design or how to maintain a database schema in the first place. In this chapter, we focus on the ER model. So that is a chapter that is the database design and the ER model. That is how to design the database, and what is the ER model, that is or how to design the database with the help of the ER model. So in this chapter, we focus on the ER data model, that is the ER model that provides a means of identifying entity that is to be representing in the database, and how these entities or how those entities are related. That is how the relationship will be maintained, or how to represent the entities with the various form, that is the ER model. So what is the entity? Any physical object, any physical thing that we can touch, that we can use, that is the entity. For example, student and the teacher, that is also the entities. And what is the relationship between you and me? I teaches you, that is the teacher teaches the student. So the relationship is the teaches. That is a entity relationship model that is represented with the help of the graphs. In the assignment that we have discussed about the class diagram, you have discussed in the, or you have done in the procedure programming assignment, as well as the next assignment object oriented. So there is a, we can say, the ER design that is also available. Therefore, in chapter 8, we consider in detail whether a set of relation schema is a good or bad database design. So in chapter number 8, we also consider the details and study the processes of creating good designs using a broader set of constraints. Right. So these two chapters are the fundamental concepts of database design. That is, what are the fundamental concepts that is related to the database design. Now 7.1 is overview of the design process. That is, what is the design process? Simply that's the overview of the designing process. So the task of creating a database application is a complex one. So whenever we create the database application, that is a complex task involving or involves designing of the database schema, that is a logical design of the database, design of the programs that access and update the data, that is how to access and how to update the data, and the design of a security scheme to control access to data. That is how to design the security scheme, or what is the designing of the security scheme that is available to control the data. So first of all, there is a database schema, that is a database logical design. Then there is a program that is used to access that schema, and then update of the information or updates the data, and the design of a security concern. So first the database schema, then design of the programs to access and update the data, then the design of a security scheme to control the data. So first of all, database schema, then designing to access and update the data, then there is a security concern that is available. So one is the database design, one is the database schema, that is a logical design, then the programs that access that schema, and the design of a security scheme or the security mechanism to control the data. The needs of the users plays an important role or a central role in the design process. In this chapter, we focus on the design of the database schema. That is, what is the database schema or how to maintain the database schema, although we briefly outline some of other design tasks that is later in this chapter. The design of a computer or the complete database application environment also meets the needs of the enterprise being model. So what is the database application environment that is available that also give the enterprise that is model required attention to a broad set of categories. Now, what are the various aspects that is used in the database that includes depend on the choices of the designs such as physical design, logical design and the view designs. So that is the overview of the design process, that what is the design process and how it is divided into multiple parts. So first is the design phases, that is the first phase is the design phase. So for the small applications, it may be feasible for a database designer who understands the application requirement to decide directly on the relation to be created. So that is the design phase. So in case of small applications, in case of small system, that is also a facility for the application programs or the application requirement that is directly deal the relationship that is to be created. Their attribute, their constraints on the relation. However, such a direct design process is difficult for a real world scenarios since they are often highly complex. Often, no one person understands the complete data needs of an application. The database designer must interact with the users of the application to understand the need of the application, represent them in a high level fashion that can be understood by the users, and then translate the requirements into low level of design. That is, the database designer must interact with the users of the application who are the users who uses the application to understand the needs, represent in a fashion that is understood by the users and translate that requirement into low level of the design. So what are the low level of the design, how to represent them, that is just giving the overview of the various structure of the database, that is what is the database look around or look like. A high-level data model serves the database designers by providing a conceptual framework in which to specify, that is in a systematic manner, what are the data requirements of the database users or what are the requirements of the database user and database structure that fulfill these requirements. That is what is the requirement, how they fulfill, and what is the basic structure, how they carry on, that is the database structure. Now, what are the various requirements or what are the various framework that is used? So first point says the initial phase of a database design is to characterize fully the data needs of a prospective database user. So first phase is that to meet or to get the end of the or to get the results of the database users or to get the needs of the prospective database user, that is what is the need of the prospective database users. The database designers need to interact extensively with the domain experts and users to carry out this task. So database designer must interact with the users, must interact with the domain experts who are the experts and who are the users to carry out the task. The outcome of this phase is a specification of user requirement. So what is the outcome? That is the specification of user's requirement. That is what is the requirement of the user. While there are techniques for diagrammatically also represent the user requirement. In this chapter, we simply focus on the how to describe in various terms, not to represent with the help of the diagrams. That is the initial phase. That is the determine the needs of the prospective database users. Next, the designer chooses a data model and by applying the concepts of the chosen data model, translate these requirements into a conceptual schema of the database. Then, first of all, gathering the requirement from the users or different users, then choose a data model. That what is the data model, and then applying the chosen data model, translate these requirements into conceptual schema of the database. So then apply the or then a designer uses or apply the concepts of data model, translate them into a conceptual schema. What is the conceptual schema that is used of the database? The scheme that is developed is at this conceptual design phase provides an overview of the enterprise. That is, what is the requirement, what is the conceptual design that is used. So first phase is gathering the requirement from the users. Next phase is designing or understanding the data model concepts. That is a conceptual data design or conceptual design phase. Then ER model, that also studied in this chapter, that is used to represent the conceptual design. Stated in terms of the ER model, the conceptual schema specifies the entities that are represented in the database. Typically, the conceptual design phase results in the creation of an ER diagram that provides a graphical representation of the schema. That is how graphically we can represent the logical design by which the database schema by which the database schema provides a method for the year mode. The designer reviews the schema to confirm that all the data requirements are in need satisfied and not in the conflict with one another. She also examines the design to remove any redundant feature. So if any redundant feature, that is a duplicate feature, is available, that is also removed. Our focus at this point on describing the data and their relationship rather than on specifying the physical storage details. So first is gathering the requirement from the users. Next is choose a data model or build a data model that applying the concept of a chosen data model. Then next is a fully developed conceptual schema that indicates the function requirement of the enterprise. That is, what is the conceptual schema, what are the various function requirement of the enterprise. In a specification of function requirement, user describes the kinds of operation, that is, what are the types of operations, or what are the, we can say, the what are the requirement of the, or what are the requirement that is given by the user. So first is the requirement gathering from the users, then next is the conceptual design, next is a specification of the function requirement, that is, what is the function requirement. That includes modifying, updating, searching, retrieving, deleting the data. Next, the process of moving from an abstract data model to the implementation of the database proceeds in two design phase. That are two design phase. One is the logical design phase. That design or the designer maps the high conceptual schema onto the implementation of the data model of the database schema or system that the system uses. Finally, the designer uses the resulting system-specific database schema in the subsequent physical design phase, that is the last phase. So the physical design of a database can be changed relatively easier than the after an application has been built. However, changing to the logical design are usually harder to carry out. So in a physical design, when the application is built, it is easier to make the changes. But if the changes that is made in the logical design, that is not that is very difficult to implement, that is very difficult to change, since they may affect a number of queries and update across the application code. So it is important to carry out the database design phase with care before building the rest of the database application. So please focus on the database design phase rather than go to the next phase for building up, for splitting up, and any phase that is available, because it is very easier to carry out the changes in the database design phase as compared to other phases. Now, this is just an introduction. What are the database design phase? What are the various phases? What are the various, we can say, the concept, that is the design phases. Now, next is a design alternative. That is, what are the alternatives for the various designing? So I'm just coming within 2 minutes. What are the various design constraints that is available, or design alternatives that is available in the database design? So a major portion or the major part of the database design process is deciding how to represent in the design or in the design process the various types of the things that is represented, such as people, places, products. So how to represent them, or how to represent in the various designing phase, or how to represent the things, places, animal, products, and the like. So we use the term entity to refer such different identifiable item. As we give the example, as I give the example to you, that there are two entities, that is the teacher and the student. So in the same way, if I want to refer the uniquely identifying the elements, that will be represented by the term entity. In a university database, example of entities would include instructors, students, departments, courses, and the course offerings. These are the various entities, that is the instructors, students, departments, courses, and the course offering. The various entities are related to each other in a variety of ways, all of which need to be captured in the database design. So various entities are represented in the number of ways that will be captured in the database design, or that will be captured in the various database design that will be followed. For example, a student takes a course offering while an instructor teaching a course offering. So there's a relationship. So student takes a course offering, whatever the course that is offered, that is taken by the student, and the instructor teaches that course that is offered by to the students. Teaches and takes are the example of the relationship between the entities. So what are the entities? That is the student and the teacher. And what are the relationship, or what are the, we can say, the relationship between the entities? That is the takes and the teaches. So a teacher teaches a student, and the student takes the option or takes the relation or takes the course. Now, in designing a database schema, we must ensure to avoid two major pitfalls, or we can say the two major limitations. What are the limitations? First is the redundancy. So there is no redundancy among the database design or among the database schema. So that is the first part, is the redundancy that is available. So a bad database design or the bad database, we can say the design process may repeat the information. So if there is a repeated information, that is not a good database, that is not a good method. For example, if we store the course identifier in the title of a course with each course offering, the title would be stored redundantly, that is multiple times unnecessary with each course offering. So it would suffice to store only the course identifier with each course offering and to associate the title with the course identifier only once in a course entity. Redundancy can also occur in a relational schema. So redundancy can also occur in a relational schema that is available. So there is a relationship, there is an aggregate relation with the course information that is offering. The biggest problem with such redundant representation of information is that there is a copies of the pieces of information that becomes inconsistent if the information is updated without taking the precautions. So if there are multiple databases, there are redundant data that is available, and if the information is updated, so precaution must be made to update all the copies of information. Otherwise, the data will be there will be data lossage, data usage, and multiple methods. Ideally, information should appear in exactly one place. There is no duplication of data, and this is one of the pitfall that is available in the database designs. Now, next part is incompleteness. That is, the database design must be complete, that is not incomplete. So that next part is the incompleteness. So it says bad database or bad design may contains or may make certain aspects of the enterprise difficult or impossible to model. So whenever we use a bad design, that makes the certain aspects of the enterprise that is difficult or impossible to model. So it is difficult to model, or it is difficult to or impossible to model the completeness, that is a bad design. For example, suppose that in case 1 above we only had entities that is corresponding to the course offerings without having an entity corresponding to the courses. So there is an entity corresponding, or there is an entity relationship that is available. So in terms of relation, suppose we have a single relation where we repeat all the courses, that is information for each section that the course is offered. It would then be impossible to represent the information about the new course. So there will be a database that is complete, that is very much complete, that does not give the problems. That is a one, we can say the dependency that is available, that is a incompleteness. Avoiding bad design is not enough. There may be a large number of good designs from which we must choose. As a simple example, consider a consumer who buys a product. Is the sale of this product a relationship between the customer and the product? Alternatively, it is the sale itself an entity that is related both to the customer and to the product. This choice, though simple, may make an important difficult or difference in what aspects of the enterprise can be modeled well. Considering the need to well choices or make choices for a large number of entities and relationship in a real world enterprise, it is hard to see that database designs can be a challenging problem or not. Now, next is the ER model. That is the next part, that is the important part. So we are finished with the two pitfalls that is available. This is the next, that is the ER model. This is a lengthy topic, an important topic also. So I'm not going to start right now. So that's all for today's session. And in the next class, that is in the tomorrow's class, I'm taking your next topic, that is the ER model. Okay, all right. So if there is any doubts, any queries, you can ask the doubts from me. So that's all for today's session. Thank you so much everyone for listening me. In the tomorrow's class, I am taking a next topic, that is the ER model, that is the entity relationship model. All right. So thanks a lot everyone. Bye bye everyone. And if there is a doubt, you can ask the doubts from me. So goodbye everyone.